So the aim of this lesson is using determinants to find the area of parallelograms and triangles. And for the warm-up question, I'll have you find, there's 3 questions. Find the area of, and for each of these I'll give you the information. So for number 1, it's a rectangle, and it has vertices 0, 0, 0, 4, and 10, 0. You can figure out on your own what the 4th corner is. The second question is, what about a parallelogram? And I'll tell you three of those points: 0, 0, 10, 0, and 3, 4. And the last question is to find the area of a parallelogram. It still has 0, 0 as one of its corners. Also has 9, 3, 2, 7, and I'll just give you the other point. It's 11, 10. So give everybody a few minutes to solve those questions. Question 3 is going to be pretty involved, and it's something that you learned in geometry 2 years ago. So give everyone time to work on that. Okay, and then I'll go over them now, but you'll give them time. So this rectangle, which has 0, 0 as its corner, and 0, 4 as its top left point, 10, 0 as the bottom right, makes this other point 10, 4. You could ask the class for that, and that would make the area base times height, which is 10 times 4, which is 40 square units. Question number 2 is a parallelogram. 0, 0, 10, 0, that's one side. That's going to be the base, which is 10. The other point is 3, 4, which is over here. Actually, we don't even need to figure out that 4th point, because the height of the parallelogram is base times height again. The base is 10, just like that rectangle from before, but the height is this line here, which is equal to 4. So this is also 40. But the parallelogram, this other parallelogram, is going to be a challenging question. There are different ways to do this question. It will probably take the class a while to answer it, but I'm going to just draw the picture to give you an idea here. 9, 3, 2, 7 is up here. 14, 10 is over there. So this parallelogram is harder because we don't really know initially the base or the height of it. And in geometry, when you took that course, you might have learned this method, where you draw a big sort of rectangle around it, and then you sort of break the rectangle up into the parallelogram, and you have some triangles, I'll call this Roman numeral 1, and some trapezoids. And by finding the area of the entire square, the whole rectangle has area. This is 14, 10. So wait, the area. This is 11, 10, not 14, 10. So 11 is the base of this rectangle. 10's the height. So the whole rectangle is 110. But then we have to figure out these 4 regions and subtract them. It turns out that 1 and 3, those 2 triangles, each have area 1/2. They're triangles, 1/2 base times height, 1/2 2 times 7. Each one is 7. 3 and there's 2 of them, so we're going to take 110 minus 14 because those are the 2 two triangles, and the trapezoids, 2 and 4, those are each 1/2. The base of the trapezoid is 3, the height is 3, and the two bases are 2 and 11. We end up with 39 over 2, but there's 2 of them, so it's minus 39. And the answer ends up becoming 57. So it's an involved question, but it is possible with some work. Well, in today's lesson, I'm going to show you how determinants have an application in this type of math, where it has up until this point, it was just some number that we used sometimes for finding the inverse or doing things with, but it didn't have any sort of geometric meaning. But today is the first time that that determinant will have some sort of geometric meaning. Let's see how that works. We've already seen how determinants can be used in geometric transformations. In other words, if I take 0, 1, 1, 1, 0 and multiply it by a point, it became xy, became yx, which was it reflected over y equals x line. We've also seen that if I take a matrix like 2, 0, 0, 2 and apply it to a single xy point, we get 2x, 2y, which is a dilation by a factor of 2. Now, you can also, and I didn't mention this, and I should have, if you have, if you're not just multiplying by xy, this thing's 2 by 2. So as long as my thing here has 2 rows, I can make my matrix have more columns. So imagine I have sort of, I'll just say x1, y1, I want to make this real generic, x2, y2, x3, z3. And if you multiply this matrix by what's now an entire matrix, this is actually a way of dilating 3 points, where this is point 1, x and y of point 2, x and y of point 3. So it would become 2x1, 2y1, 2x2, 2y2, 2x3, 2y3. So what this would accomplish is, if I actually had my original points here and they made some sort of triangle, and I multiply this matrix by this matrix that's formed by putting the 3 points, the vertices of the triangle, and arranging them in this way, down, each point becomes a column, what ends up happening is the answer are the 3 points, the 3 vertices of the entire, of the triangle that got dilated. One type of transformation that we haven't talked about much, if these two numbers are different from each other, I get 2x, 3y. Now, if you apply that to a single point, like 2, 0, 0, 3, applied to 10, 2, it would end up becoming 26. And it's not clear kind of what's going on. But if I apply it to an entire shape, let's say I apply it to the square, the unit square, that has 0, 0, 0, 1, 1, 0, 1, 1 as its 4 corners. And when I do that, look at what happens. If I then graph these 4 points, the square gets sort of stretched into a rectangle. This is sometimes called, I think it's called a shear. So it's not quite a dilation because the x and y stretches are stretching different amounts, but this square turns into a rectangle. And just this square, this will be relevant later, the original square had an area of 1, whereas the new rectangle has an area of 6. Just something to notice, the determinant of 2, 0, 0, 3 happens to be 6.